In this video, we are going to talk about redox reactions, which involves oxidation and reduction. We will be also practicing how to write half equations. I will also go through some rules about oxidation numbers, as well as doing some further practice questions. In the end, we will be discussing how to write complex redox reaction under both basic and acidic conditions. So let's begin. The definition of redox reaction is a transfer of electron from one species to another. Essentially, it is a reaction about transfer of electron. And combustion reaction is one type of redox reaction. The old definition of redox reaction is as follows. Oxidation means gain of oxygen, hence the term oxidation, and loss of hydrogen. The way I remember this is that hydrogen is always like the opposite to the oxygen. So if you are gaining oxygen, you are also losing hydrogen when you are doing oxidation. And reduction is loss of oxygen. And the opposite of that is gain of hydrogen. This is very useful for organic molecules. So the old definition is useful in identifying redox reaction for organic molecules. For example, the combustion of methane, which is natural gas, is actually an oxidation reaction, as we have discussed before. So, what is getting oxidized and what is getting reduced? We can use the old definition to figure it out. So the only carbon-containing compound is methane and carbon dioxide. So they must go together. So methane has basically become carbon dioxide after this reaction. So it has lost hydrogen. So CH4 becomes CO2, and simultaneously it gained oxygen. So from this definition, we know that methane gets oxidized. Now we look at the oxygen gas. So oxygen gas have lost one oxygen and gained two hydrogen. So following on this definition, it is getting reduced. In fact, for this type of combustion reaction involving hydrocarbons, the fuel is always getting oxidized, and oxygen is always getting reduced. It does not make any sense to oxidize oxygen, since oxygen is used to oxidize other stuff. So you cannot oxidize oxygen gas anymore. So that's the old definition. So the new definition is about electrons, and this applies in general. So for the old definition, it only applies to a very narrow range of reactions. So the new definition, oxidation is defined as loss of electrons. Reduction is defined as gain of electrons. And this is true everywhere. Even for this combustion reaction, after we learned about how to write half equations and rules regarding oxidation numbers, you can see there's actually transference of electrons going on. So a very important definition which you need to remember. How do you represent redox reaction? You use half equations. So for this example, this is like the complete equation. We cannot see any transference of electrons. So that's why we need half equation. So half of what is going on to see the which species is getting oxidized and which species is getting reduced very clearly. So imagine we have the reaction, very simple reaction, like this. So the magnesium atom have turned into magnesium ion. So this is ionic substance. So essentially composed of these two ions. And because we need to balance the charge, so magnesium itself have 0 charge. Magnesium ion have positive 2 charge. So we need 2 electrons to balance out this charge. And because magnesium atom have lost 2 electrons in the process of becoming magnesium ion, it is getting oxidized. Or it has undergone oxidation. Similarly, we know that the chlorine gas have turned into chloride ion. So this part have a charge of -2. So we also need to make the left-hand side -2 charge as well. We do this by adding 2 electrons. Because it is gaining electron, this is reduction. And if we combine those two together by basically add them up, we see that the electrons cancel out. So there's actually no electron involved in the complete equation. That's why half equations are very important. It allows us to see clearly where the electron is from and where the electron actually went to. A point I want to emphasize: electrons can't be created or destroyed. It can only be transferred. And the implication of this is that oxidation and reduction must occur at the same time. So whenever you have reduction, you must also have oxidation, because we cannot just create electrons from nowhere. It is only a process of transference of electrons, not about creation or destruction of electrons. And because of this important definition, we can create more terminologies. So this is actually a very confusing terminology for many students. Oxidizing agent. So oxidizing agents causes oxidation. In other words, it causes other species to lose electrons. And because we know that redox reaction is essentially a process of transferring electrons, so if something causes other things to lose electron, then itself must gain electron. And gaining electron by definition is reduction. So itself is actually getting reduced. Another way to think about this problem is that the electron lost from the other species is getting transferred to the oxidizing agent, meaning it is gaining electron, hence it's getting reduced. Reducing agent. It causes reduction. So it causes other species to gain electron. And where does this gaining of electron come from? It comes from itself. So itself must lose electrons. And when something loses electron, by definition, it is getting oxidized. In summary, oxidizing agent is getting reduced. Reducing agent is getting oxidized. Maybe it's helpful to get some practice. For this chemical reaction, we can see that the copper atom have become copper ion. To balance the charge, it must have lost 2 electrons. And here, to also balance the charge, it must gain 2 electrons. So based on the definition, copper atom is getting oxidized. And Fe2 plus ion, because it's gaining 2 electrons, it's getting reduced. Because copper is getting oxidized, it must causes other thing to be reduced. So this electron released must have a destination to go to. I don't care where the destination is, but some species must be accepting these 2 electrons. In this case, it's the Fe2 plus ion who is accepting these 2 electrons. So it causes the Fe2 plus ion to undergo reduction. Thus, it is the reducing agent. And it's the other way around for Fe2 plus ion. Because it is gaining electrons, it must causes another species to lose electrons. So it must causes the other species to undergo oxidation. So it is the oxidizing agent. We can also write the overall equations by just add equation 1 and equation 2 together. We can see the electrons cancel out. So we get exactly the same equation as the one above. Now let's move on to a very important concept. Oxidation number. In the real world, it's very hard to see this kind of chemical reaction, where it's involving simple ions and simple atoms that you can just figure out who is getting reduced, who is getting oxidized by looking at it. The reality is much more complicated. So oxidation number, do not think of this as a burden to you, as something you need to memorize. Of course, you need to remember or to know how to apply this, but it is actually a tool. So it's like a pen or a pencil. You need to learn how to use them. And once you know how to use them, it becomes very, very helpful to you. So it is the tool that helps you identify redox reactions. And this is useful for complex redox reactions. Here are the rules. The first rule, pure elements. So I will abbreviate oxidation number as ON. I have oxidation number of 0. The silver atom, hydrogen gas, oxygen gas, chlorine gas, all have oxidation number of 0. Anything you can think of, sodium, potassium, all 0. Because they are pure elements. Second rule, oxidation number for simple ion is equal to the charge. For example, magnesium ion, the oxidation number is 2. Aluminium ion, oxidation number is 3. I should emphasize positive 2 and positive 3. Chloride ion, oxidation number is negative 1. The third rule, oxidation number for hydrogen is mostly 1, plus 1. Except when it is combined with group 1 metals like sodium, lithium, things like that. And in this case, it has oxidation number of negative 1. The reason behind this is actually explained in the 7th rule. I will cover this rule very shortly. Oxidation number for oxygen is mostly -2, except when you have the peroxide ion. In this case, the oxidation number is -1. So H2O -1, 2 times 1. So in this case, hydrogen has oxidation number of 1 because hydrogen is not group 1 metal. Carbon dioxide, oxidation number for oxygen is -2, and we have 2 of them. To balance the charge, since this is overall neutral, we need +4 as the oxidation number for carbon. Hydrogen peroxide, because it is peroxide, perhaps we can infer from the hydrogen that the positive charge is +1 times 2. So this part must have a charge of -2. Since we have 2 oxygen atoms, each oxygen atom should have a charge or oxidation number of -1. Barium peroxide. There are 2 valence electrons for barium, so it wants to lose 2 electrons. Hence, the oxidation number should be +2. To balance the charge, since this is overall neutral, the oxidation number for O2 must be -2. This implies that the oxidation number for oxygen is -1. Number 5. The sum of oxidation number for neutral molecule is 0. So I have actually used rule number 5 to explain this to you. For example, methane. It is a neutral molecule, so the sum of oxidation number should be 0. We know that the hydrogen have oxidation number of 1, and then we have 4 of them. To balance this, the oxidation number for carbon must be -4. For CO2, we know that it's overall neutral. Oxidation number on oxygen, -2 times 2 is -4. So this must be, oxidation number on carbon must be +4 to balance the charge. Why isn't the oxidation number for oxygen 1? Because it is carbon dioxide. There's no peroxide in the name. So it is not peroxide ion. It's actually 2 times this ion, not peroxide. It's oxide ion. Number 6. For polyatomic ion, the sum of oxidation number is equal to the charge. For this one, oxidation number for oxygen is -2, so we have 3 of them. This is -6. And overall, the charge is -1. So the oxidation number for nitrogen must be +5. And +5 minus 6 is -1. For CO3, 2 minus. For this, we know the sum is -6. So the oxidation number on carbon must be +4, because overall it is -2. 4 minus 6 is -2. SO4 2 minus. This is -2 times 4, which is -8. We know that overall it is -2. So the oxidation number for sulfur should be +6. 6 minus 8 is -2. The last rule. Most electronegative element get negative oxidation number. In this example, the sodium ion or the sodium atom, we know that it only has one valence electron. So it really wants to get rid of this valence electron. So in this case, the hydrogen atom is actually more electronegative than sodium. That's why sodium takes the value of +1 and hydrogen takes the value of -1. Because hydrogen is accepting this electron. So that's all the rules for oxidation number. The key is to do practice questions. And you should, the goal is that you don't need to look up those rules. And whenever you see something, you can immediately know the oxidation number. Speaking of practice, let's try to do some practice ourselves. Determine the oxidation number of chromium. So because this is a pure element, the oxidation number is 0. And because the charge on a simple ion is just the charge of ion itself, the oxidation number is just the charge of the ion itself, it should be +3. For this one, it's more complicated. If we look at the oxygen, we know the oxidation number is -2, because this is not a peroxide. -2 times 4 is -8. Since the overall charge is 0, so the charge on chromium must be +8. The oxidation number for chromium must be +8. For this one, let's have a look. Let's do the oxygen first. -2 times 7 is -14. And the overall charge is -2. So 14 plus 12 is -2. So the sum of oxidation number for chromium must be 12. Since there are 2 chromium present, you divide by 2. So the oxidation number is +6. For this one, again, -2 times 3 is -6. And overall, 0 charge. So we know the sum of oxidation number should be, the other side, it should be +6. +6 divided by 2 should be +3. For here, -2 times 3 is -6. Overall 0 charge. So the oxidation number should be +6 for chromium. So this compound does not actually exist. I have copied down this incorrectly. So the actual compound should be this. So it has a overall -1 charge. And we follow the same procedure. -2 times 4 is -8. Because overall, we have -1 charge. -8 plus 7 is -1. So the oxidation number on chromium is +7. So now let's move on to see whether the following reaction is redox reaction or not by using oxidation number as a tool. So for this one, hydrogen is +1 times 2. So oxidation number for sulfur should be -2. Chlorine gas is neutral, so oxidation number is 0. Sulfur is also neutral, oxidation number is 0. And here, hydrogen takes the value of +1. Chloride ion is -1. So the oxidation number for chloride have decreased from 0 to -1. Oxidation number for sulfur have increased from 2 to 0. Now remember, a decrease in oxidation number is reduction, because you are getting more negative. How do you get more negative? By gaining electrons. So that's why it's reduction. Increasing oxidation number is oxidation. You are increasing your charge. So the only way to do that is to lose electron. That's why it's oxidation. So using the fancy terminology we have learned, the oxidizing agent, it's something that is being reduced. So it's chlorine gas. Reducing agent, something that gets oxidized. It's the sulfide ion in H2S. So let's have a look of this example. We know that this is -1. Oxygen is almost always -2. Oh, sorry, hydrogen should be +1. So -2 times 4 plus 3. Overall, this is neutral. Should be 5. Oxidation number for P should be 5. For KOH, we know that K must be +1, since it is a group 1 metal. OH overall have -1 charge. So O is -2, H is 1. Here, K is still +1. Thus, the PO4 ion, you can derive this based on the charge for potassium, but the PO4 ion actually have a charge of -3. So oxygen is -2 plus something is equal to -3. And this something must be 5. Oxygen -2, hydrogen +1. So as you can see, the oxidation number is not changing. So this is not redox reaction. That's why oxidation number is very useful. Because if you don't know the rules, then there's no way you can figure out whether this is a redox reaction or not. Next example, natural element 0. And here we know it's +2. You can either see this from the periodic table, or if you know that the charge on NO3 is -1, you can know that the charge of magnesium ion in this case should be +2. This natural element 0. Because this have a charge of -1, the silver ion has a charge of 1. So we have a decrease of oxidation number for silver, which means it is getting reduced. Hence, the oxidizing agent is the silver ion. Increasing oxidation number for magnesium, it is getting oxidized. Hence, it is the reducing agent. Reducing agent, magnesium. A very familiar combustion reaction. Natural element 0. -2, 1. We know hydrogen have +1, and we have 4 of hydrogen, and overall charge is 0. So to balance this, we must have -4 for carbon. Here we know the oxygen mostly always -2. Overall, carbon dioxide is neutral. So it must be +4 oxidation number for carbon to balance out the negative oxidation number of 2 oxygen atoms. So the oxidation number for carbon increased from -4 to 4. Increase means it is getting oxidized, which we know is true as fuel always get oxidized. Hence, it is causing other stuff to be reduced. So it is the reducing agent. Oxidation number for oxygen decreased from 0 to -2. So this is reduced, meaning it must causes other species to be oxidized. So it is the oxidizing agent. After some practice questions, let's now get back to the main topic. So the last thing I want to talk about in this video is writing complex half equations. So let's first talk about in acidic conditions. You will be told in the exam whether they want you to write complex half equations for acidic or for basic, under acidic or under basic condition. So whenever they give you any indication that this hydrogen ion is present in the system, you know it is under acidic condition. So there's actually a formula for you, or a rule that you must follow. It's called the Kohl's rule. The K stands for you need to balance the key element first. So the key element is anything except hydrogen and oxygen. They are very special. Then you balance the oxygen by add H2O. Then you balance the hydrogen by add the hydrogen ion, because we are in acidic condition. Then you add electrons to balance charge. Then you add the state. Remember, electron does not have any state. So let's do a practice. From MnO4 to Mn2 plus under acidic condition. So the key element is actually balanced already. We have one on the right, one on the left. Now let's balance the oxygen. We have 4 oxygen on the left. We need 4 on the right by adding 4 H2O. Now let's balance the hydrogen. We have 8 hydrogen on the right, so we need 8 on the left. Now let's balance the electrons, balance the charge. So the charge on the right is +2. The charge on the left, 8 minus 1, is 7. So how do you get from 7 to 2? By adding 5 electrons. And we have already added the state. Remember, electron does not have any state. So as you can see, this is actually a reduction half equation because we are gaining electron. So the other side of the story. So this one should be oxidation. So this is ethanol. And we do not like this form because we have hydrogen hanging here. It's easy for us to see it is an ethanol, but not really easy for us to see how many hydrogens are present. To solve this problem, we write it in a slightly different way. Now it's very easy to see how many hydrogens we have. Key elements already balanced. Now let's balance the oxygen. Great news, already balanced. Now let's balance the hydrogen by adding the hydrogen ion. So we have 6 on the left, we need 2 more on the right. Now let's balance the charge. 0 overall charge on the left. So we need to add 2 electrons to ensure the right hand side also has 0 overall charge. And then we add the state. Those are small chain hydrocarbons. Not really hydrocarbons, but like small carbon chain. So they are soluble in water. So great, this is actually oxidation. We can also see from this directly, we are losing hydrogens. So it must be oxidation based on the old definition. So that's the 2 half equations. We need to combine them by making sure we do not have any additional excess electrons. So now we have 5 electrons in this reduction process and only 2 electrons in this oxidation process. This is not going to work. There's no way we can create 3 electrons from nowhere. So we need to balance this by multiplying the top by 2, the bottom by 5. So now we have 10 electrons in this reduction, and also 2 times 5 equal to 10 electrons for this oxidation. So great. And now let's combine them together. So on the left hand side, we have 10 electrons plus 18 hydrogen ions 5 ethanol. So this is what we have. We can cancel out the electron. The electron should always cancel out in your complete chemical reaction, because we should not be creating or destroying any electrons. We have 10 hydrogen ions on the right, 16 on the left. So we can cancel this one out, and this 16 becomes 6. And the rest are all balanced. So that's how you're writing the complex half equations. Under acidic conditions. Now let's do one on the basic conditions. So we have lots of OH minus ions, hydroxide ions, for this chemical equation. So the idea is you do everything as normal. So you do everything as if it's under acidic condition. So to the key element, already balanced. Oxygen, not balanced. We need one more by adding H2O. Hydrogen not balanced. We have 2 on the right, so we also need 2 on the left by adding H+. Electron also not balanced. The left-hand side is neutral, so we add 2 electrons to balance the charge. Now it's looking good, but remember we are under basic condition, not acidic. What we do is we add OH ion to essentially balance out this hydrogen ion. So we have 2 hydrogen ions on the left, so we add 2 OH minus ion. So we also need to do this on the right hand side as well. So what is this? What is H plus OH? So this is 2H2O. So they combine to form water. So it should look like something like this. And we have 1 water on the right, 2 on the left. So we can cancel out one of them. So the left hand side, the charge is -2. Right hand side charge also -2. So now we add the state. And it is now a balanced half equation. And in fact, this is the reduction half equation. So the only difference here is that you are adding OH to combining with H plus ion to form water. The rest should be exactly the same as under acidic condition.